Hello everybody, and welcome back to another geometry lesson. Today we're going to take a look at section 10.2, which is all about arc measures. Now, an arc is a shape that is circular, but doesn't cover a full circle, something like this. When we talk about arcs, we are talking about a portion of the outside of a circle. So it's fitting then that we should start with a circle. Unfortunately, this is a really bad center. Let's call this center C. There we go. When we are talking about an arc, we mean a portion of a circle that is cut up. So allow me to split this circle into a couple of pieces. Let's call this point A, this point B, and this point C. We could make an arc between any of these 2 points. A to B would make an arc. B to C would make an arc. Even A going all the way around to C would make an arc. All of these count. So let's talk about first how we can classify these arcs. And to do that, we need to talk about the central angle. The central angle of an arc is an angle whose vertex is the center of the circle. So if I was to build an angle here, let me color it in green, maybe an angle that looks like this would be our central angle. Let's call this angle 120 degrees. Well, what we've done here by making this angle is we've actually created 2 different arcs. One arc is something we would call the minor arc. And it's called the minor arc because it is the one that is inside of this angle. A minor arc is essentially an arc that is less than 180 degrees. A minor arc is an arc whose central angle is less than 180 degrees. We could call this minor arc AB, or the abbreviation for an arc is to put a little arc over the 2 letters. This means arc AB. If we were talking about how big this arc is, the measure of an arc in degrees is the same as its central angle. So since the central angle here is 120 degrees, we could say the measure of arc AB is 120 degrees. This isn't the same as the length of the arc in like inches or centimeters or miles, but it is how we're going to measure them for right now. Well, where there's a minor arc, there's also going to be a major arc. And the major arc is what's left over, or what's outside of the minor arc. So if we were making this major arc, the major arc would go from A through point C all the way to point B, right? We could call this major arc. And since minor arcs use 2 letters just to go from point A to point B, major arcs are going to use 3 letters to distinguish them. This is going to be ACB. Arc ACB. Now, if I asked what the measure of this arc is, many of you would be able to pick it up already. The key is that a circle has to add up to 360 degrees. So if the minor arc is 120 degrees, then the major arc should be what adds up to make 360. In that case, it'd be 240 degrees. So the major arc of a circle is an arc whose points do not lie on the corresponding minor arc. Whenever you split up a circle, you are always going to get a minor arc and a major arc. And the major arc is just all the points that are not in the minor arc. Perfect. Finally, when we take a look at a semicircle is a half of a circle. So a semicircle is an arc whose endpoints are the endpoints of a diameter. An example of this I will draw up here. Let's say we've got a circle here, and we've got diameter d. A semicircle would be the arc that covers all the points through that diameter. Perfect. So let's take a look at exercise 1. For exercise 1, we are trying to find the measure of each of these arcs. RT is a diameter, so keep that in mind. Let's start with the measure of RS. RS has an internal, or a central angle measure of 110 degrees, so the entire arc here has a measure of 110 degrees. Simple enough. But things get tricky now. What if I wanted to find the measure of SRT? Well, first off, it has 3 letters, so we are talking about a major arc here. It's going to be the arc that goes all the way around from S to R, all the way over to T. This red arc is arc SRT. And that seems very difficult to calculate. There's a couple of ways to do this. One way is to note that RT is a diameter, which means that this arc here, from T to R, is a semicircle. It's 180 degrees. If you want to go this route, then S to R is 110, R to T is 180, we end up getting 290 degrees. The other way to do this would be to recognize that, again, RT is a diameter, so these two have to add up to 180. TS then would have to be 70 degrees. I'll mark it in blue. This central angle would have to be 70 degrees. And a major arc is just the supplement of a minor arc. If this is 70 degrees, the entire arc around it that is not 70 degrees is whatever's left over, 290. Finally, for TSR, we've already deduced that TS is going to be 70 degrees, and since TSR is a semicircle, it's covering exactly up to the diameter, we know that that's going to be a semicircle, a 180 degree arc. Love it. Next up, we've got the arc addition postulate. The arc addition postulate is a lot like the segment addition postulate, and we sort of already used it in this last example. The arc addition postulate says this: the measure of an arc formed by 2 adjacent arcs is their sum. In other words, if you have an arc here that's, 45 degrees, and you have an arc that's right next to it, that ends up being, let's call that 135 degrees, then no matter what, you can add these two arc measures together to get the entire arc. The entire arc here would be 180 degrees. Fantastic. Beyond this, there are just a couple more definitions I want to cover before we do the last examples. Let's start by talking about congruent arcs. Now, we want to be very careful. Even though two angle measures could be the same, it does not mean that the two arcs that they're on are the same. What do I mean by that? Let's say we have two circles, one small and one large. And let's say I gave them both 90-degree internal angles, or central angles. If I gave them both 90-degree central angles, their arcs would certainly both be 90-degree arcs, right? I mean, this one would be 90 degrees, and this one would be 90 degrees. But the key is this. This arc here on the right is clearly way bigger than the arc on the left. They're not congruent because the circles are not congruent. The circles have different radii. This one has a small radius. This one has a larger radius. So, there's two conditions for something to be a congruent arc. And these ones are not congruent. Congruent arcs must have the same angle measure, have the same measure, and they must be arcs of congruent circles. Or on the same circle. So two arcs will be congruent if they have the same measure and they're both either arcs of the same circle or on congruent circles. Which brings us to what a congruent circle really is. Two circles are congruent if and only if they have the same radius. Two circles are congruent. I'm going to use IFF to represent if and only if. That's the abbreviation. If their radii are congruent. Perfect. Finally, we have this last theorem called the congruent central angles theorem. And it works like this. Let's say we have one big circle here with the following center. And I tell you that I've got two diameters cutting through here, like so. And I'm going to label these points A, B, C, and D. A, B, C, D. Well, we know that anytime we make an X like this, we create vertical angles, right? If these two angles are vertical, it means that these two arcs are congruent. So that's what the congruent central angles theorem says. It says, two minor arcs are congruent if and only if their corresponding central angles are congruent. Two minor arcs on the same circle will be congruent if and only if the two corresponding central arcs are congruent. So let's take a look at some examples. Exercise 2 is going to ask us to find the measure of each arc where, RT is not a diameter, and this is now our central circle R. So, sorry folks, this is a typo. But we're trying to find the measure of each arc of circle R. This time we don't have a diameter though. So let's take a look and see what we can do. The measure of GE is going to be the arc that stretches from G all the way to E, and we know it's going to be the shortest distance because it's a minor arc. If it only has 2 letters contained, we're talking about the minor arc, not the arc that goes all the way around the major arc. Since GH is 40 degrees and HE is 80 degrees, this is just going to be 40 plus 80 degrees, or 120 degrees. Now, if we were trying to find the measure of arc GEF, be careful. We are not talking about the arc that goes from G to F this way. We're talking about the major arc. So we know it's going to be the bigger arc, the one that loops all the way around from G to E all the way to F, the one that I've marked in blue. Once again, we can add up all the minor arcs that are contained within and see what we get. So GH is 40, HE is 80, and EF is 110. This is just 40 plus 80, plus 110. When we add all these together, we get 230 degrees. Perfect. Finally, now we're asking for the minor arc from G to F. I'm running out of space to write these arcs, so I'm sort of writing them on the inside, but you get the picture. The idea is we want to find the arc that goes from G all the way to F. And the good news is we already know the major arc that goes from G to F. If the minor arc, or the major arc that goes from G to F is 230 degrees, the minor arc is just what adds to that to make 360. In this case, 230 plus 130 makes 360. Very nice. In exercise 3, we're trying to decide if the following arcs are congruent or not. So we were just given this statement that PQ is supposed to be congruent to SR, and we have to make that decision. Remember, the only way to decide if 2 arcs are congruent is if they are on congruent circles. In this case, it's just one circle, so it's automatically congruent to itself. And if their central angles match. We see that this central angle is 65 degrees, but could we find out this central angle? Well, PS is a diameter. We could tell because it's just one straight line that goes all the way across. So no matter what, arc PS, the entire arc here, is 180 degrees. We can do 180 minus 65 minus 50 to make the measure of arc SR. And when we calculate this out, we actually end up getting that the measure of arc SR is 65 degrees. Well, hang on a second. Since this central angle is 65 degrees and this central angle is 65 degrees, that means that this statement is true. Both of these arcs have the same central angle measure, so they are congruent. These two are the same length. What about JK and NM? Well, if we take a look at example B, we have 2 circles now, so we have to be super, super careful. It looks like JK and NM both take up about 1/4 of their circle. However, unless these 2 circles have the same radius, in other words, if the 2 circles are congruent, that's the only way that these 2 arcs will be congruent. Well, let's take a look at the radii of these 2 circles. The radius is given here in circle O. It's 6. Our radius equals 6. But what about in this circle, circle P? Well, we're given that the diameter is 12. Recall, folks, that a diameter is 2 times a radius. So if 12 is the diameter, the radius is half of 12, which is 6. Aha! These two radii are, in fact, the same length. So these are congruent circles. If we have two congruent circles, we have two congruent arcs. Very nicely done. So this one is also going to be true. JK is congruent to NM. Finally, let's take a look at UT and SR. Now, we have something here called concentric circles. Concentric circles happen when a circle is inside of another circle. So we have this smaller circle inside of a larger circle. And we're trying to compare the two arcs, TU and RS. The good news is, we know the central angle is absolutely going to match. Both of these arcs have an arc measure of 90 degrees. The question is, are they congruent? And we can tell very clearly from their sizes that, no, this inside one is going to be much smaller than the outside one. Why? Because the radii of these two circles are different. The radius of the smaller circle is QR. The radius of the larger circle is QU. Almost looks like double the length of QR. These two arcs are not congruent. Let's take a look at exercise 4 and see what we can do here. Now we are solving for x, and then solving for the indicated arc measure. So our end goal here is to find the measure of arc RST. And since it has 3 letters, we know that we're talking about the major arc from R to S to T. Well, we know that the measure of RST is made up of a 6x degree angle and a 7x degree angle. So 6x degrees plus 7x degrees, which we know is going to be whatever 13 times x degrees are. The problem is we don't know what x is, so we're sort of stumped, right? Well, not exactly. In this problem, we have all of the angles across the entire shape, all the arc measures. We know that a circle has to add up to 360 degrees total. In other words, we can just add together each of these arcs, each arc here, and it should add up to 360. So 360 equals 4x plus 6x plus 7x plus 7x. All we need to do is solve for x here. When we add 4 plus 6, we get 10, plus 7 is 17, plus another 7 is 24, so 360 degrees equals 24x degrees. All we need to do here is divide by 24, and we will know exactly what x is. So we do 360 divided by 24, and we end up getting 15 degrees. X is 15 degrees. So we've solved for x. Let's take that up here and plug it into our equation. The measure of arc RST is going to be 13x, where x is 15. So when we multiply this all out, we end up getting 195 degrees. That's the measure of angle or arc RST. Perfect. I want you to actually pause the video here and give B a shot. I'm going to warn you, not all of the angles, not all the arc measures are marked off, but they are all known in this problem. Pause the video here and see what you can do. Hopefully you've had a chance to pause the video and take a look. Let's see what we can do together. So we're looking this time for the measure of MAN, the measure of angle man. This one looks like it could be a semicircle, but I'm just not sure, to be honest with you, because it could be a little bit inaccurate. But there is something that can help us here. The fact that AM is x degrees and NB is x degrees means those two arcs are congruent, right? Well, anytime that two arcs are congruent, their central angles are also congruent. Wait a second, if we have two congruent angles, and these are two lines that cut through them, doesn't that automatically make these vertical angles? Because these are vertical angles, we know for a fact that these are diameters. MAN is 180 degrees. We just have to solve for x. Since these are vertical angles, we know that vertical angles come in pairs. We know that this 4x degree angle and this 4x degree angle are the same. So the measure of this arc is also going to be 4x degrees. If we want to solve for x, we know that 360 equals x plus 4x plus x plus 4x. 360 equals 10x, and 360 divided by 10 is 36. So x is 36 degrees. Very nice. Last, most certainly not least, let's take a look at exercise 5. So in a survey of hikers across Michigan, participants were asked what their favorite modes of transportation were. And spoiler alert, most of the hikers liked walking. This pie chart organizes their responses, and we need to find the measure of each minor arc. There's one itty-bitty teensy-weensy little problem here. In this exercise, we were not given any angle measures. Well, Mr. Strager, but I see 43 right there. That's not 43 degrees, that's 43%. Uh-oh, pie charts are always in percents. Well, what can we do here? Anytime we are trying to convert between two measurement systems, one thing that we could always do is set up a proportion to compare. To show you what I mean, let's talk about what makes up this full circle. So, if we were talking in terms of percents, in total, percents make up 100 in a circle. 100% is a full pie chart. What about degrees? Well, in a full circle, degrees make up 360. There's 360 degrees in a circle. Because these are both total amounts, we can set up a proportion like we did in Unit 8 and compare. So if I wanted to figure out what degree marking arc AD would be, we can just, well, actually, let's do AB since that's the first one. In percents, it's 24%. In degrees, we don't know. So we can set up a proportion and solve. We're comparing 100% to 360 degrees, because both of those are the full circle. 24% to x degrees, since that's what the car will take up. When we cross multiply and solve this, we end up getting x times 100 equals whatever 24 times 360 is. And in this case, 24 times 360 gives us 8640. When we divide both sides by 100, we end up getting the exact percent. X equals 86.4 degrees. So the measure of arc AB is 86.4 degrees. That's how much of the circle the car portion takes up. Another way to think about this is we're trying to see exactly what portion of this circle is taken up by the car. We know that 24 out of 100 is being taken up by the car. That's the fraction that we could compare to 360. So get this as a decimal, and that will be exactly what portion is being taken up. 24 out of 100 is going to be 0.24. Multiply that by 360, and you will get the same answer. 0.24 of 360 is 86.4. I want you to pause the video here and try out the other portions of this circle. I want you to see what the measure of each minor arc is. Pause the video and give it a shot. How'd you do? These are the measures of each of the minor arcs of this circle. And with that, you're now ready to take on the homework. Thank you so much, everybody. Have a fantastic rest of your day, and I'll catch you next time.